Hello, I hope you guys are having a great day. Today we're going to be doing our domain range continuity notes. I'll start off with a few definitions. So first off, a relation is a set of ordered pairs, and I can give you an example of what that would look like. So you would enclose the set within curly brackets, and then you just list your points of ordered pairs. So I'll put a few here as an example. And then when you're done listing all of the coordinate points, you're going to put the curly bracket again. So this is a set of ordered pairs or a relation. Now, the domain is the set of all the x values in a relation, and you have to read those from left to right. Remember that coordinate points are written as x comma y. So the first number in the ordered pair will represent the x values that we need for the domain. So I'm going to come to the relation we had done before, and I'm going to underline every single x value because those x values are the ones that are going to be in the domain. And then they have to be from left to right on the coordinate plane. So on the left hand side you have negative infinity, on the right hand side you have positive infinity. So you do have to go from left to right, starting with the smallest numbers and going towards the biggest numbers. So I see the smallest number here we have is 1, and then we have 4, 7, and 9. Okay, and that's in increasing order. We can do the same thing for the range. So the range is the set of all the y values in a relation. Again, x comma y is a coordinate point. The second number represents the letter y. So these right here will be the y values that we're going to use to write our range. And just like the domain, they're going to be from smallest to greatest, from low to high, bottom to top, however you want to remember that. So the smallest number we have is -3, then 0, then 2, and finally 3. Okay, so I'm going to make a little note here for you so that you don't forget that you need to write these in increasing order. So always the smallest numbers first, biggest numbers last. Okay. Another definition we have is a function. A function is a relation where each element of the domain has only one element associated with it in the range. You can also do this graphically using the vertical line test. All this means is that you can only have one y value for each x value. So I'm going to write that down for you. Only one y value, only one y value for each x value. And we'll practice doing the vertical line test in a minute. Okay, so those are some definitions for you. Now let's go get started with different ways to represent a function. So I have written here 4 different ways. We have graphically, numerically, algebraically, and words. You have seen all of these in your previous math classes. So graphically is just a points on a coordinate plane where you have input values on the horizontal axis and the output values on the vertical axis. Numerically, on a table or a set of ordered pairs. Algebraically, by an equation with 2 variables. And then words, you're just verbally describing how the input variable is related to the output variable. Anyway, I just wanted to throw that in there, but you have seen that before. Maybe not in those words, but you have been exposed to all of those representations of a function. Okay, so we'll get started with our first example, which is y equals x squared. So the first thing I want to do is create some points for us. So I'm going to start off by making a little table on the side with x comma, not x comma, just x and y on the table. On the right hand side, we usually just put y, but here I'm going to be very specific and write the equation so we know what we're going to be plugging into. Okay, notice that my coordinate plane doesn't have any values, so I'll just put a few. I'm not going to put a bunch of them. And then these same x values on the x-axis, I'm going to put them on my x column on the table. And they have to be in increasing order, so from left to right, starting with -2 all the way to +2. Okay? Now to find what y is going to be, notice that this x is going to be correlated to this x right here. So whatever we have on our x column, we're going to be plugging into the right. So if x is -2, I'm going to plug -2 into here. Okay, -2 squared is +4, -1 squared is +1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So now that I have some points, I can go and plot them on our graph. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so -2, +4, -1, +1, the origin, 1, 1, and 2, 4. Now, if you remember from, hold on, let me focus on this line. It's gonna come out all wonky anyways, but okay, you get the point. If you remember from algebra 2, when your equation is x squared, that's a quadratic. A quadratic function makes a parabola. Mine looks more like a V, but it should be more of a U shape. It's just really hard to draw it. But anyways, okay, so after now that I have the graph on my coordinate plane, I'm going to perform the vertical line test to test whether or not it is a function. So if I draw a vertical line anywhere along this function, you see that it only touches the line one time. So it touches once here. If I draw it over here, it only touches one time. I draw it here, it touches once. Here, it touches once. So it passes the vertical line test, meaning that it is a function. If it would have touched 2 or more times, it would have failed the vertical line test. Okay, so that's our first example of a function. Moving on to our next example, which is x equals y squared. Notice that this one we don't have y equals, and usually we work with y equals, so all I'm going to do is solve for y. Now, to get rid of that square, I will have to do the square root, and if I do it on the left, I have to do it on the right, and vice versa. So what happens, the square root and the square cancel out, leaving you with just y, and then you have the square root of x left over. But every single time you take the square root of a number, you do have to do plus or minus. The reason for that is because you can have two negative numbers that make a positive, or two positive numbers that make a positive. So for example, I could have -3 times -3 is +9, and similarly +3 times +3 is still +9. So you have to account for the fact that the numbers going in could have been negative, or they could have been positive. Okay, so there are two different cases. That's why it is essential to put the plus or minus symbol when you take the square root of a number. Okay, so just like before, I'm going to create a table. I'm going to put x on the left-hand side and y equals plus or minus the square root of x on the right-hand side. Okay, I'll put the same values as before, from -2 to +2. Okay, now we're going to be plugging in this -2 into the square root. Now I can go to a calculator really quick and do the square root of -2, and notice that it comes out as an error because it's not a real number. The reason for that is because you cannot have a negative underneath the square root. So these two negative values will be undefined. Now you can take the square root of 0 though. So if I take the square root of 0, that just gives me 0. Okay? The square root of 1 is 1, but we do have this plus or minus. I didn't add the plus or minus to the 0 because 0 doesn't have a sign because it's in the center. But 1, I will do the plus or minus 1, and then so the square root of 1 is 1, and then plus or minus the square root of 2, which we can approximate to a decimal. So again, I have a square root of 1 is 1. You can see that there. The square root of 2, if I approximate this to a decimal, approximate to convert to decimal, enter. So it's approximately 1.41. So approximately equal to plus or minus 1.41. So now that I have some points, I can put this on my table as well. On my coordinate plane. So we start at the origin. We have at x equals 1, we have +1, but we also have -1. And at 2, we have positive 1.41 and negative 1.41. And so it kind of creates this sideways parabola. This should be more rounded, just like the other one. It kind of came out a V again, but you know what I'm trying to draw, I hope. Okay, so that's what the graph looks like. And basically what that creates is that the top half of that is the positive square root of x, and the bottom half is a negative square root of x. Okay, so now let's perform the vertical line test. So if I draw a vertical line, notice that it touches once and twice. Everywhere I draw this vertical line, it touches more than once. And so for that reason, this function fails the vertical line test, and it's actually not a function at all. So I'm going to say not a function because it fails the vertical line test. Okay, so here you have an example of a function and a graph that is not a function. Okay, so we'll be moving on now to domain restrictions. So we're going to cover a few different types of graphs here. We're going to start off with the square root function, then we're going to do rational, and then finally we're going to do logarithms. So these have the most common types of domain restrictions. So we'll start off with the square root. You know this is a square root function because it has the square root in front of it. And as you can see here, if you have a negative number under the square root, it will come out as undefined, which is what I had said earlier. That number or whatever values are inside of the square root is called a radicand. That's a new vocabulary word for you. The radicand inside the square root must be greater than or equal to 0 in order for it to be defined. Okay, so greater than or equal to 0 is either 0 or a positive number, right? Anything greater than 0 is a positive number. We need to set it greater than or equal to 0 because if it was less than 0, that would be a negative number, and a negative number is undefined. So what we're going to do is grab the radicand inside of this first example, which is 3 minus x. You don't need to grab the square root. All you're going to do is grab the radicand and set it to be greater than or equal to 0 and solve for x. So here I can add x on both sides. And negative x, positive x creates a 0 pair. Then we bring down the 3, bring down your sign, and we have x. 0 plus x is x. If we want to write the x first, which is most commonly what we're going to be doing, you will have to flip the inequality sign. So for our answer, we got x is less than or equal to 3. Another method you could have done it, and it just depends how your mind works. There's always more than one correct way to do things in math. Instead of adding the x, you could have subtracted the 3. So 3 minus 3 cancels out. It's a 0 pair. You bring down your negative x, bring down your inequality sign, and 0 minus 3 is negative 3. Now remember, there is an imaginary 1 in front of this negative x. So to get rid of that negative, you will have to divide everything by a negative 1. Negative 1 divided by negative 1 is 1, which cancels out, and then you bring down everything else. When you divide by a negative, though, your inequality sign also has to change, and then negative 3 divided by negative 1 is positive 3. So I'll make a note of this so you don't forget it. It's a common mistake that kids forget. So switch the inequality sign. When dividing by a negative number. Okay, switch the inequality sign when dividing by a negative number. Now what we're going to do to visualize how this graph is going to look like, I am going to draw a number line. And like I said earlier, on the left-hand side, you have negative infinity, and on the right-hand side, you have positive infinity, and in the center, you have 0. So because our domain was x is less than or equal to 3, I'm going to start off with just putting a 3 on my number line, a positive 3 on the number line. Now, here's a little review in case you forgot from last year. I'm going to write this at the top of the page so you can use it later. Okay, so a review, if you have open circles versus closed circles. Open circles, in interval notation, you're going to be using parentheses. In closed circles, you're going to be using brackets. In inequality notation, you're going to be using less than or greater than when it's open. And when it's closed, it's less than or equal to or greater than or equal to. Okay, so there's your little review. Write that down and study it. And then so I'm going to be using that to do my number line. Okay, so this symbol was less than or equal to. So the equal to implies that it's going to be a closed point at 3, and then less than 3 means it's going towards negative infinity. Okay, so my domain in interval notation, always going from left to right, will be negative infinity to 3. Okay, negative infinity to 3, and that's where it stops. Now, how am I going to close this? So the 3 that has a closed point will have a bracket. For the infinity, infinity will always have a parentheses. The reason being is that we do not know the value of infinity. Infinity goes on forever and ever and ever. So since we can't put a value, a number on it, it's going to be open. Whether it's negative infinity or positive infinity, always use a parentheses. Okay, so the domain here is negative infinity to positive 3. Okay, moving on to another example. Here I have n divided by o equals undefined. So a good trick that I have for you is to think of 0 on the top is okay, but 0 on the bottom is a no-no. Okay, 0 on the top is okay, 0 on the bottom is a no-no. The reason for that is because 0 in the denominator gives you an undefined value. Okay, let me give you an example in the calculator. So I can do 0 divided by 10, and that will give me 0. But if I do the same the other way around, 10 divided by 0, okay, 0 on the bottom is undefined. Okay, so you can see it here. 0 on the top is 0. It's okay. 0 on the bottom is undefined. It's a no-no. Okay, so I'll make a note here as well. Your denominator cannot be 0. Okay, your denominator cannot be 0 ever. Okay, so we have our first example of a rational function. You know it's a rational function when there is a variable or 2 in the denominator. So we have to start off with factoring this. Now I'll start off with giving you the equation of the standard form of a quadratic function. You'll remember this from last year. Ax squared plus bx plus c. Okay, so you need a, b, and c. So I'll do a equals, b equals, and c equals. And those are referring to the coefficients. Okay, so in front of x squared, since there is no number, remember there's an imaginary 1. So a would be 1. And the same thing for b, there's an imaginary 1 being multiplied by x. And then c would be negative 2. Okay, and then you can do x method. And I'm going to have a whole video dedicated to factoring as well in case you don't remember this. In the top of the x, you're going to do a times c. At the bottom, you're going to put b. And on the side, you're going to do a times x. And then figure out what two factors multiply and add up. Okay, so a times c, that's a times c. 1 times negative 2 is negative 2. And then b, which is positive 1. So what two numbers multiply to negative 2 and add up to positive 1? Those two numbers would be positive 2 and negative 1. I will be erasing this a at the bottom because I've already identified a to be 1. Okay, and then I don't really need to do 1 times x because 1 times x is just x. So I'll just leave it simplified like this. Okay, so I have now my two factors. So I'm going to come over here and simplify this. Notice that I didn't factor the numerator, so I'm going to leave the numerator alone. I'm going to just rewrite it, but the denominator, I will be writing it as my two factors of x plus 2 and x minus 1. Okay. Now notice that I can simplify this further. I have a common factor at the top and the bottom of x plus 2 that I can cancel out, and then I will be left with 1 over x minus 1. Okay, so notice that this x minus 1 was in the denominator, so it does have to stay in the denominator. Please do not make it a whole number. And then additionally, if you have canceled everything in the numerator and there's nothing left up here, just put a placeholder of a 1. Okay, so there are a few different things going on here. So we have a whole, and we also have a vertical asymptote. I'm going to come off to the side of the page to give you the definition of a whole. Okay, a whole I'm sorry for the noise. They're doing construction or something next door. A hole in the graph occurs when the same factor appears in the numerator and the denominator. Okay. Another word that you might remember from Algebra 2 is a vertical asymptote. Vertical asymptote, you find it. Vertical asymptote is found by setting the simplified denominator equal to 0. Okay, so two different things are going to be happening on this function. So the first part is the whole. So notice there was a common factor of x plus 2 in the numerator and the denominator. So that will be our first discontinuity. Okay, so what you do to find the whole is whatever factor you canceled out, you're going to set it equal to 0. Okay, so you solve this, subtract 2, so x equals negative 2. So there's a whole at x equals negative 2. The next thing you're going to do is find the vertical asymptote by grabbing the simplified denominator. So this is the most simplified. So x minus 1 being the denominator, I'm going to set that equal to 0 and solve for x. So I'm going to add a 1. So x equals positive 1. Okay, so these are discontinuities. So a whole, think about it as if there is a line and I'm literally going in and taking a point away from the graph. So this point is basically now missing and it's no longer there. So that's a whole. A vertical asymptote is an imaginary line going through a function where basically the graph will never touch. Okay, so remember it gets really, really, really close to that line, but it will never be equal to the vertical asymptote. Okay, so I'm going to create the number line, negative infinity on the left, positive infinity on the right, 0 in the center. But here we have two numbers. I have one at negative 2 and positive 1. So negative 2 and positive 1. Okay, so a whole is basically a break in the graph. There is nothing there. So if there's nothing there, it will be an open circle at 2. Okay, and at 1, which is the vertical asymptote, like I just said, you will never ever touch the vertical asymptote. You're never equal to the vertical asymptote, so this one will also be open. Okay, now rational functions, again, rational functions is when you have a variables in the denominator. Rational functions, the domain of rational functions is all real numbers except where you have a whole and except where you have a vertical asymptote. Okay, so this one will go all real numbers, so everywhere except the whole and the vertical asymptote. All real numbers except the whole and the vertical asymptote. Okay, so now to write this domain in interval notation, you always start from left to right. So on the left hand side, you have negative infinity, and remember you always use parentheses with infinity, comma, negative 2, and that open circle will also make us use a parentheses. Okay, to put different pieces of the domain together, you're going to use the unison symbol, which is the letter U. And then we have our next little piece of the domain from negative 2 to positive 1, parentheses for the vertical asymptote, union 1 to positive infinity. Okay, so again, we went negative 2, we had to stop there. From negative 2 to 1, we had to stop again, but then we kept going from 1 to infinity. Okay, so this will be the domain of this rational function. Okay, let me give you another example of a rational mixed with a square root function. So notice we have a square root function in the denominator. Now, This may or may not look familiar to you, but the square root of 3 minus x was the first example we did, square root of 3 minus x. So I'm not going to redo the problem. I'm just going to write down the answer that we had, which was x is less than or equal to 3. Okay. And I'll come back to that. Now I'm just going to focus on the denominator. So with rational functions, the first thing you need to do is try to factor and simplify. But regardless of how I factor this, I will probably never see the factor of square root of 3 minus x down here at the bottom. So if nothing cancels out, then there is no whole. Okay, so if there is no whole, that means that this entire denominator will have to be my vertical asymptote. And you find the vertical asymptote again by setting the denominator equal to 0. Now when you have two binomials multiplied like this, the only way to solve for x is to split them up. I know a lot of kids, the first thing they want to do is multiply using FOIL or the box method, but that will overcomplicate the problem when you can just split it up like this and solve for x. Okay, so on the left hand side you can add 1 and you get x equals 1. On the other side you're going to subtract 2. And after you subtract 2, you're going to divide by 2. And then you're going to take the square root of x. But remember, you can't have a negative number under the square root. So this one is undefined. So the only one that's going to matter is that vertical asymptote at x equals 1. Okay. So this is where it gets a little complicated when you have two different functions like this. So I'm going to create the number line again, negative infinity to positive infinity with 0 in the center. But I'm going to hover my points. So I'm not going to put the number lines on the actual graph. So I'm going to start with that number 3 from the numerator, and then also the positive 1 that we had from the denominator. Okay, so for the numerator, it was less than or equal to 3. So at 3, I'm going to make a close point. And again, I'm not going to overlap them. I'm going to make them separate. So on the floating above the number line, I have the numerator less than or equal to 3. For the denominator, remember all real numbers except the whole and except the vertical asymptote. But we don't have a whole here, so it'll be all real numbers except the vertical asymptote at 1, which is an open circle because, again, you never touch the vertical asymptote. You just get really close to it. And then it goes infinitely in the other direction. Okay, now the final answer will be only where these two lines overlap. So what I'm going to do is shade in where they overlap, starting with the negative infinity side on the left. So notice that I have both green and pink here, so they are overlapping here. And I'm going to keep shading. They overlap, they overlap, they overlap. And then right here, I have a point on the pink line, but not the green line. So I will be stopping there, but I can pick up after the vertical asymptote, and they keep overlapping until I get to 3. So even though the green line keeps going, there's no more pink. So since the pink stopped, the whole domain is going to stop as well. And then so the domain will only be represented by the shaded areas. So from negative infinity, comma, positive 1, parentheses on both of those, union from 1 to 3, and then 3 is a close point, so I will be using a bracket at 3. Okay, so the domain is negative infinity to 1, 1 to 3. Okay, another type of graph we can have are logarithms. So logarithms always have numbers in parentheses after them, and if the number inside the parentheses is negative or 0, it will be undefined. This value inside the parentheses is called an argument. Okay, so the argument of a logarithm has to be positive. Okay, so if it has to be positive, what I'm going to do is just set it greater than 0. Now again, the stuff inside the parentheses, so this whole thing right here will be the argument. So x minus 5 is the argument. Okay, so I'm going to take only the argument, ignore the other stuff. The argument itself has to be positive. Okay, it cannot be 0 and it cannot be negative. It has to be greater than. Okay, because again, log of 0 or log of a negative number will give you an undefined value. Okay, and then just solve for x. So the only way to do that is to add 5 on both sides. So x has to be greater than 5. Okay, I'm gonna make my number line again. Then I have 5. Now 5 will be an open circle because that inequality sign does not say equal to. It just says greater than. Okay, so at 5 it will be an open circle and it's greater than, meaning it's going towards positive infinity. Okay, so that domain will be 5 with a parentheses to infinity, also with a parentheses. Okay, so that is a logarithm example. The next page, we're going to talk about types of discontinuities. So the most common type of graph that you've seen are continuous, which is the first example. You can think of continuous as being able to draw the function without ever having to lift up your pencil. Okay, so this is an example of continuous. Removable, there are two different types of removable. So you can see here there are two different types. This one has a defined point. This is just an example. They're not always going to look like this. But there's essentially some kind of hole. So you see the hole right here. But then at the same x value of a, there is another defined point. Okay, so on the same value of a, you have an open circle and a closed circle. So that's a type of removable discontinuity, but it doesn't always have to be like that. So this one just has a hole, but that one would still be considered a removable discontinuity even if it doesn't have the defined point. And more often than not, these are the type that you're going to be seeing when we do rational functions. On the ACP, they do use the words interchangeably. So removable discontinuity is the same thing as a hole and vice versa. So on a question, if they ask you where's the removable discontinuity, you need to know they're asking you for the hole, and vice versa. Okay, another type of discontinuity is called jump. So a jump discontinuity is essentially on the same exact value on the x-axis. There is a literal jump. So it started down here and it jumped up, or it could jump down. So let's say this was inverted like this and then it just went down here. So it like just jumps down, but it has to be on the same x value. We're going to practice these in the near future, but not right now. What we are going to focus on as well is infinite discontinuities, which is essentially just a vertical asymptote. So you can see that along the line of A, there is a vertical asymptote where the graph gets really, really close to it, but it doesn't ever touch it. Okay, so this is a vertical asymptote, and just like with the hole, they might ask you on the ACP where is the infinite discontinuity, and you need to know that that's the same thing as vertical asymptote. Okay, so when we do rational functions, these are the two most common types of discontinuities that we're going to be solving for. But yes, we'll do that lesson in a while, in a little bit. Okay, then I have some examples for you. So find the domain and range for each, sketch the graph, and state the type of discontinuity. Okay, so 4 divided by x. When you have a variable in the denominator, remember that's a type of rational graph. When you do rational graphs, the first thing you want to do is try to simplify. But 4 doesn't divide by x. They're not common terms, so there is no whole. Remember, the whole only occurs if you have a common factor in the numerator and the denominator, but nothing is going to cancel out here. So the other type of discontinuity is a vertical asymptote, which is found by setting the denominator equal to 0. Okay, the denominator is x, you set that equal to 0. This one is pretty simple because you don't have to solve for x, it's just going to be equal to 0. So on my graph, I'm going to go and do a dashed line at x equals 0, which is going to represent the vertical asymptote. Okay, vertical asymptote at x equals 0. So I'm going to create a table of points. Now notice that there are a lot of points from negative 8 to positive 8. I'm not going to do that many because that's a lot. Maybe I'll start at like negative 4 or something. Let's graph this on our calculator and see what we can get. Okay, so start with the division symbol with the fraction. 4 divided by x. Okay, and then I'm going to graph this, and this is what the graph looks like. Now I want to pull up the table, so I'm going to do menu, table, and then split screen table. Okay, it always starts at like 1 or 0, but I'm going to scroll up on the x value so I get some negative values. So I said I would start at like negative 4. So at negative 4, y is negative 1. Oops. Okay. At negative 3, I'm gonna skip that one at negative 3 because it's a decimal and it's kind of hard to graph. So I'll just jump down to negative 2, negative 2. And then it was negative 1, negative 4. Okay, let's see what else. At 0, notice that it's undefined at 0. That's because that's where we said the vertical asymptote was. So at 0, it is undefined. And then, let's see. So at 1, 2, and 4, so I'm going to skip 3 again because of that decimal thing. But 1, 4, 2, 2, 4, 1. Okay, so 1, 4, 2, 2, 4, 1. So there are some points that now I can use to sketch the graph. So negative 4, negative 1, negative 2, negative 2, negative 1, negative 4, 1, positive 4, 2, 2, and 4, 1. Okay, now another thing we haven't really talked about, but you can see on the graph, is a horizontal asymptote. Okay, so we've talked about vertical asymptotes, but here you can see the graph doesn't touch horizontally. How do I make this go away? Sorry. Oh, there it goes. So it doesn't ever touch past 0. So you can see I can keep zooming this out and it just gets closer and closer to the line on the x-axis, but it never actually crosses past it. So for that reason, my horizontal asymptote is also at y equals 0. So I'm going to add that to my graph as well, so that when I graph it, I don't go past y equals 0. And this is for the horizontal asymptote, y equals 0. Okay, so I can make my function, just sketch it. Gosh, that was so ugly, sorry. Okay, so it looks something like that. So you have the vertical asymptote, the horizontal asymptote, and then you have some points there. Okay, now the next thing we need to figure out is what the domain will be. The domain again is negative infinity to positive infinity on the x-axis. So from negative infinity, I'm going. I don't have to pick up my pencil until I get to this vertical asymptote. Once I have to pick up my pencil, that will create a break in my domain. And then after this break, I pick back up after the vertical asymptote at 0, and then notice that I keep going on forever. So I only had to pick up my pencil one time at x equals 0. So the domain will be all real numbers except 0. And parentheses again, because the vertical asymptote, you never touch it. Okay, now the range is read bottom to top. So starting from the bottom, I'm touching the graph. I can follow it, I can follow it, I can follow it until I get to 0. Again, after I pick up my pencil, that's going to create a break in my domain, in my range. But after I pick back up at y equals 0, I don't have to pick up my pencil anymore because it goes all the way up to infinity. So the range here will also be all real numbers except 0 because of the horizontal asymptote. Okay, and remember that vertical asymptotes are the same word, the same meaning as an infinite discontinuity. Okay, so this is a type of infinite discontinuity. You can see the vertical asymptote. Okay, so that's the first example. Let's do another one. So here we have, again, another type of rational. We know it's rational because of the variable in the denominator. So what you have to do is first try to factor and simplify the fraction. Now that numerator is a case of difference of squares. So if you take the square root of both of these, you get Let me draw my two factors. So the square root of x squared, so if I take the square root of x squared, I get x, right? So x and x, because the square root and the square cancel. Now if I take the square root of 16, that would give me plus or minus 4. Remember that every time you take the square root of a number, you need to do plus or minus. So I get positive 4 and minus 4. Okay, if you don't remember how to do difference of squares, there's a video that I'll upload on that as well. Okay, and the denominator, we didn't have to factor it. It's already simplified as x plus 4. And as you can see, this x plus 4 cancels out with the denominator. So all I have left is x minus 4 divided by 1. Okay, so I do know there's going to be a whole. So let me solve for the whole. Remember, that's where you set the common factor that you cancel out equal to 0. So at x equals negative 4, there will be a hole somewhere in this graph. To find the y-coordinate, and I'll teach this more in depth in a little bit, in a few lessons, but to find the y-intercept, not the y-intercept, sorry, the y-coordinate of the hole, all you have to do is plug this x into the simplified function. Okay, so y would be equal to negative 4 minus 4 over 1, which is negative 8. Okay, so again, this x value goes into this x value. So that's where I got negative 4 minus 4 over 1. Okay, so the whole will be at negative 4, comma, negative 8. So I'll put an open circle at negative 4, negative 8, because that is where the whole is going to be. Okay, and then usually there is a vertical asymptote as well when you have a rational function. Remember, the vertical asymptote is when you set the denominator equal to 0, the simplified denominator, and the simplified denominator here is 1. And you set that equal to 0, but that's never going to be true. So if that ever happens where you just have a number and no variable, you will have no vertical asymptote. Okay, so all we have here is a whole. So I'm going to do the same thing as before, which is to create a table. And I'm just going to put this straight into the calculator. So I'm going to start off with the fraction, x squared minus 16 in the numerator, and at the denominator I have x plus 4. I'm going to press enter, and you see you get a line. So I'm going to pull up the table, menu table, okay, and we have some values here. So at negative 4, where it's undefined, that's where we said the whole is going to be. So that aligns with what we have already discovered. And then notice that they're just going up by ones. So we'll just copy this on our notes. So I can have negative 5, negative 9, negative 4 is undefined, negative 3, negative 7. I'll just jump down to 0. I'm not going to put all these numbers. And then 3. I'll just put a few values on here just so I have an idea of what to plot. Negative 5, negative 9 is somewhere like down here. Negative 3, negative 7. They're just random, you guys. I just picked random points from the table. There's no reason. Just didn't want to pick a bunch of them and put a bunch of points on my paper. Okay, so this is going down, this is going up, and it is a line with a hole at negative 4, negative 8. Now notice that the calculator did not show this hole. The only way you can even try to figure out if there will be a discontinuity is if you pull up the table and it says undefined for the y value. So the thing with the calculators is that they are helpful for graphing in the table and you can see the asymptotes, but you will never see the whole. So if you rely solely on the calculator for these types of problems, you will probably get it wrong because you'll never know where the whole is. Okay, so it's best to try to do it by hand first and then try to confirm on the calculator. Okay, so reading the domain from left to right, I have negative infinity. I stop at the negative 4, and then I pick up after negative 4 to infinity. Okay, so from left to right. I'm going, and at -4 I have to stop, but then I keep going on forever. Now coming in from the bottom, I'm coming in from -infinity, and I have to stop at -8, but after -8 I keep going on infinitely. So that the range will be -infinity to -8 and -8 to infinity. Okay. Now this one had a hole, it didn't have a vertical asymptote, and the type of discontinuity that is called removable. So this one is a type of removable discontinuity. Okay. Third example, the absolute value of x over x. Okay, let's go ahead and graph that. So I'm going to open up a new graph. Oops. Start off with a fraction, the absolute value of x divided by x, and I'm going to press enter. And I get a graph that looks like this. I'm going to pull up the table as well so I can get some points. So on the negative side, I have all negative ones. There's something going on at 0, and then after the positive numbers, it's all +1. Now notice this is a type of jump discontinuity. So when it got to the y-axis, it jumped from -1 to +1. So that's going to be the type of discontinuity here. It just jumped up. So let me make a table. I'm not going to put a bunch of points, but I'll put a few. Okay, so remember when it was on the negative side of the x-axis, it was all -1. It was undefined at 0, but then afterwards it all went to +1. Okay, so because it's undefined at 0, that means that there is no point at all that is closed because it's undefined. If it was a closed point, it would give me the number where it is defined, but it's undefined. So both of the points will be open when it goes from -1 to +1. Okay, and then it's defined all the way through -1 and +1 on either side of the y-axis. Okay, so again, these have to be open circles because it's undefined at 0. So I don't know, it's just not there. It has to be open. Okay, so the domain of this one coming in from the left hand side will be -infinity. And there is not any point that is defined at 0. There are 2, but they're open, so that is not included in the domain. We have to stop there and split up the domain, but then we pick back up after 0 and we go on to infinity. Okay, now for the range coming in from the bottom, notice that there's nothing here. The graph only exists here and here. So because those are constant lines with nothing here, nothing is here, nothing is up here, to represent the range of constant lines, you're going to be using curly brackets. So I can say with a curly bracket, the range exists at -1, and it also exists at +1. Or I can say -1, close the curly bracket, union, and then +1, curly bracket. Man, my curly brackets are struggling. There you go. It could be like that, or you could also just use square brackets instead of the curly brackets. So you can say, -1 union +1 with closed brackets on both of them. All of those will be acceptable answers when you have a constant function. Constant means that it doesn't go up or down, it's just straight. Okay, and like I said previously, this is a type of jump discontinuity. Okay. Another example I have for you, another rational function. So again, with rational functions, the first thing you need to do is try to simplify by factoring. I can't factor x anymore, and x minus 2 is already simplified. You can't just cancel this, like that would be incorrect. Imagine this is in parentheses, okay? So x is different from x minus 2, so those are not the same factor, so this one has no hole. However, there is a vertical asymptote when you set the denominator equal to 0. Okay, so x minus 2 equals 0. You add the 2, and you see that you're going to have a vertical asymptote at x equals 2. So I'm going to draw a vertical line down x equals positive 2. Okay. And now we can pull up the table on the calculator so we can sketch it. So fraction x in the numerator, x minus 2 in the denominator, and you get a graph that looks like this. So again, we haven't really talked about how to find the horizontal asymptote yet, but you can see it visually on the screen. Notice that the graph is never going to touch y equals 1. So the horizontal asymptote is at y equals 1. So I'll put that on my notes so that I make sure I don't go past. So I don't go past y equals 1. Okay. Now I can pull up the table, menu table, split screen table. And a lot of these have a bunch of decimals, so I'll just put some decimals, maybe the ones that are more exact and not repeating. So like negative 6.75 looks good. Let's see what else. Maybe negative 2 and 0.5, 0, 0, 1, negative 1. Let's see what else there was. At 2, it was undefined. So remember, it's undefined at 2 because we have a vertical asymptote, and then 3, 3, 4, 2. Okay, that's enough. All right, so let's just try to plot this. So at negative 6.75, so like right here, negative 2.5, the origin, 1, negative 1. 2 is undefined, and then 3, 3. And then we had another one at 4, 2, I believe, that I didn't add. 4, 2. Yes, 4, 2. Okay, and then I'll just follow the points. And remember not to go past the asymptotes. You get really close to them, but you don't touch them. Okay, so there is what the graph looks like with the asymptotes. Again, there was no hole on this one. So the domain is going to be all real numbers except the asymptotes. So the domain, negative infinity to 2, and then from 2 to infinity. So all real numbers except the vertical asymptote, and the range is all real numbers except the horizontal asymptote. Okay, so on the x side, I never have to pick up my pencil until I get to x equals 2, and then I keep going after x equals 2. So again, the only break is at x equals 2. For the range, I go from negative infinity, so bottom to top, and I keep going from negative infinity to 1, and then I have to pick up my pencil after 1. So when I have to pick up my pencil, that creates a break. So the break here is at 1 for the range. And a vertical asymptote is the same as an infinite discontinuity. Okay, so that is the set of notes. I hope that it makes sense. I also have another worksheet, graphically how to find domain and range. So I'm going to focus on domain first, and then I'll come back around and do the range. Okay, so for the domain, remember that you're reading from left to right. And for the range, you're reading bottom to top. Okay, and then remember, for open circles you have parentheses, and for closed circles you have square brackets. Okay, okay, so let's start with the first example. So I'm going to be doing the domain first, okay? So this arrow right here, what that means is that this line is actually going down forever to negative infinity. I'm trying to make a straight line and I'm struggling. Okay, whatever. So this goes down to negative infinity. Anytime you have any type of arrow, that's going to be going to infinity, okay? What I'm going to be doing on the on my graph is I'm going to be shading where I see the function, okay? And I'm going to start from left to right. So on the left, I have the function, I have graph, and then somewhere right there, I have to stop, okay? So I have points here, I have points here, I have points here, I have points here. So that's why I have shaded this in pink. But when I get to this value, I don't have any points. There is something here, but it's open. So if it's open, it's missing. So it's not going to be included in the domain. So I do have to stop there. And then I don't have anything again until I get to that close point right here. Okay. So when I get to that close point, I'm going to keep going. So notice I have points here, 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 here. Okay, and then right here, when x equals -3, there is something else going on. There is an open circle, but then also a closed circle. When you encounter something like this where you have an open versus closed, it's almost like that open one doesn't really matter that much anymore. When you're writing your domain, you only need one defined point. You only need one closed point in order to keep going with the domain, okay? So because I have at least one defined point here, I do not have to stop and I can actually keep shading. And this line here also goes on infinitely. Okay, to positive infinity. So because again, I have a closed point here, even though this one is open, that one doesn't really matter. I do not have to stop. So I'm gonna keep going all the way to infinity. Okay, so the only time I actually had to stop is when it was open and there was nothing defined. And then I didn't shade here because notice that in all these grids, there was no function. Okay, it was blank here. So I didn't shade there either. Okay, so now let's write this in interval notation. From left to right, I started with negative infinity. And remember, infinity always has parentheses. And then this was 1, 2, 3, 4, 5, 6, 7. From -7, it stopped. Parentheses because it's an open circle. Union. And then at -6, it started, but it's closed. So this one will be a bracket. And then it never stopped. We kept shading all the way into a positive infinity with a parentheses there. Okay, so negative infinity to -7, from -6 to infinity will be the domain. Okay, let's do another one. So again, this arrow tells me that I'm going negative infinity, and this arrow here tells me I'm going towards positive infinity, okay, on the x-axis. So I'm going to shade everywhere that I see the function. So from negative infinity, now when I get here, I'm going to analyze. There is an open circle, but a closed one as well. So I'm not going to stop there. Remember, you just need one defined point to keep going. Okay. Then I reach another type of something going on here. Again, we have an open circle, but a closed one. So when that happens, if you have at least one closed, you can keep going and not have to break up the domain. And that one goes on infinitely. So you can see we never stopped shading. So this domain will be all real numbers, negative infinity to positive infinity. Okay, let's do another example of domain. So we have arrows going towards negative infinity, and this arrow at the bottom going towards positive infinity on the x-axis. Okay, so I'm going to shade where I see the graph, so starting from negative infinity, but then something happens here. What is this? So I will have to stop here because we have two open circles. Nothing is defined at all, so I will have to stop there, okay? But I'm going to keep shading where I see a solid line. So this will be considered part of the function. It is solid. So right after that break, I will keep going, okay? Now we have another discontinuity here, open versus closed. I can keep going because there's at least one defined point. And as you can see, it keeps going on forever to infinity. So the only break that we're going to have is right here where there were two open points, which is at 1, 2, 3, 4, 5, 6, 7, 8, negative 8. Okay, so our real numbers accept negative 8. Okay, so that is that for domain. Now I'm going to do the same thing, but I'm going to do the range. Okay, so the range is read from bottom to top. I'm going to erase these infinities here because they're backwards for the range. Okay, the reason I say they're backwards is because on the x-axis this is negative infinity and positive infinity, but on the y-axis down here I have negative infinity, and at the top we have positive infinity. Okay, so both of these arrows here are going down towards negative infinity this time. Negative infinity, negative infinity. Okay, so I'm going to be shading from bottom to top. So because this graph extends all the way to negative infinity, I will start shading all the way from negative infinity, and I'm going to go up, 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 up. So I keep seeing the function all the way through. Okay, but I'm going to stop right there, and I'm going to observe, is there any other line at y equals negative 2? And if I go over to the left, I see that there's another point, okay? When I do y equals negative 1, there's another point here. When I go to 0, there's another point here. So notice that even though it appears to be empty right here, we do have points on the left-hand side. So I actually don't have to stop shading, and I'm gonna keep shading, let's say until 0, and then let's keep analyzing, okay? So if I observe at 0, I have a point here, and I also have a point here. So I don't have to stop. At y equals 1, I actually have 3 points, 1, 2, and 3, okay? I'm actually only gonna stop when I get to y equals 2, because there's nothing else after 2. Whoops. After 2, there is nothing left. You can see that this red square is empty, okay? So the range from bottom to top will be negative infinity until 2, and with parentheses because both of these were open, okay? So negative infinity to positive 2 will be the range. Okay, let's try that again on the second example. So on this side, I'm going up to positive infinity on the y-axis. This one at the bottom though, notice that it's a constant line, so it's actually never going to go down to infinity. It's just going to stay here at y equals negative 3. It is actually never going to go up or down. It's just going to stay there forever. Okay, so let me shade where I see the function. So I don't have anything at negative infinity. The first time the function appears is at negative 3. Now I didn't go up because there is a break. Notice that between this grid line in all these squares, there is no function. There's no solid line, okay? So it actually picks back up right here at negative 2, okay? And then from negative 2, I can observe. So even though there's an open circle, there is a closed one at the same line. Okay, so I don't have to stop there either. So that's the same concept as when we were doing the domain. As long as there's one closed for every y value, you don't have to stop. So the same thing here at y equals 2, there's an open, but there's also a closed on the same line. So I don't have to stop. And this one does go up to infinity. So I'm going to keep shading all the way to the top to positive infinity. Okay, So now how am I going to write this range? So remember earlier I said if you have a constant line, you're going to represent that range in a set of curly brackets. So it was constant at -3. And we do curly brackets. Usually the domain and the range will tell you where you start and where you stop. Okay, that's why there's two numbers, a starting point and a stopping point. We started at negative infinity, we stopped at positive infinity. But when it's constant, there is no start or stop. It's just always here. Okay, it doesn't go up, it doesn't go down, it's just constant. So that's how we represent it in curly brackets by itself. Okay, and then union, and I'm gonna pick back up at -2, and it's closed at -2, so you don't always need to have a little closed dot for it to be closed. As long as it's a solid line like that, it's solid, it will be defined there. The only time you'll have an open circle is if you actually see the open hole on the graph. Okay, and then from -2 we kept shading all the way until positive infinity. Okay, so that's that range. Okay, let's do our last example. So starting from bottom to top. So again, this extends down to negative infinity, and on this side it goes up towards positive infinity. Okay, so with my highlighter, negative infinity, I'm going to keep shading until I don't see the line anymore, which is about right there. And I actually don't see anything after that until we get to y equals 1. And after y equals 1, I don't see anything either until we get to y equals 3, and then that's when it goes up to infinity. Okay, so be mindful that between these two squares of the graph, it is absolutely empty. Okay, that's why I did not shade right here. I didn't shade there because there's nothing there. And the same thing here. Between these two, there is no function. That's just the x-axis, so don't get that confused with the actual graph. That's not the graph. So I didn't shade here either because there is no function. So now let's write the range. So from negative infinity to -1, and that's going to be a bracket because of that closed point, union. And then it's a constant line, so that's going to be a curly bracket at +1, union. And then from 3 parentheses, because that's a hole at y equals 3. And then it goes up to infinity, okay? So I have some more examples for you guys to practice. You have 3 there and 6 at the bottom. So you can practice this on your own. Reminder that all you need is at least one defined point for you to not have to split up your domain. Okay, I hope you have learned so much about domain and range, and I'll see you in the next video. Bye.